Hi, here we are discuss about a project FPGA implementation of spectrum clock generator with Onion Modulation. So here the spectrum clock generation SSCG is used in electronic to intentionally modulate the frequency of the clock signal. This modulation is achieved by spreading the energy of the signals across a range of frequencies rather than concentrating it a single frequency. This primary purpose of using a spectrum technique in clock generations is to reduce the electromagnetic interference and improve the electromagnetic compatibility in electronic systems. In this context of the spectrum clock generation, the primary motivations of using various layers of modulations, regardless of whether the term of Onion modulations is used is to provide more sophisticated and flexible approach to electromagnetic interference reductions. The most important key design of the onion wave in that the central part of the waveforms and the smallest slope, and its purpose is to make the output. To achieve the best design of the frequency effect, the traditional method uses the memory ROM to control the slope to realize the onion waveform. The existing approach requires a large amount of memory area and complex design, and it consumes more power consumptions. This proposed approach introduced a novelty based architectures for onion modulations with a less logic sizes and power consumptions. This architecture designs using Verilog HDLs and simulated using Modelsim and synthesized using a Xilinx Vertex-5 FPGA. Now we can verify the base paper and the architecture. So here this is a reference paper we have chosen for this approach, spectrum clock generations using the piecewise linear modulations. Okay, so here we have proposed with using this abstract document. Okay, so here this is a proposed abstract document, and here this is a reference architectures, and we have built up with this architectures. Okay, so here this is a figure 5. Okay, so here this is a proposed architectures. Okay, so here we can give an input signal V1 and V2 and clock 1 and clock 2. Okay, so here V1 and V2 is a constant one, and clock 1 and clock 2 is a different clock frequencies. Compared to clock 1, the clock 2 is more than 4 times of clock 1. Okay, so here the output signal we are taken from OWV. Okay, and here internal architectures you can refer, it will support with the number of additions, subtractions, and registers, and 2 controller. Okay, so as per this architectures we have developed a proposed architectures. Okay, so this architectures we have developed with the Verilog HDLs and simulated with the Xilinx Vertex-5 FPGA. Okay, so here, so this is a reference waveform. It will be given in figure 7. Okay, so here so this is a Verilog HDL coding part, and this is a simulation output. Okay, so here this is an onion waveform. Okay, so it will be designed using 32.23 kilohertz range. Okay, you can refer it. Okay, and this part we have synthesized using a Xilinx Vertex-5 FPGA. So here you can analyze the number of slice registers, number of LUTs, and number of occupied slices, number of IOB bonded. Okay, and synthesis report you can check delay. Okay, so here delay equal to 4.433 nanosecond. Okay, and you can verify the RTL schematic. So this is a proposed architectures we have developed it. Okay, so here V1, V2 we are given an input, and it will be given to the adder and subtractor unit. Okay, so adder, subtractor, 3-bit register, and non-linear up down counter, online modulations control, accumulators, and onion ROM modulations we have used. Okay, so here the power consumptions, it will be take 0.829 volt. Okay, and we have written the detailed architecture notes for this project. Okay, so here you can analyze it. Okay, finally it's come up with the literature survey and references. Okay, thank you.